So we're in section 10.1, and we're talking about 3D coordinates. So 3D coordinates are just like 2D coordinates. We just have one more number. So everything's pretty much the same. We just add one more number. That one number can sometimes make things a lot more interesting. So our 3D coordinate system, what we're going to do is take our x-axis and our y-axis, and we're going to turn it sideways. So we call this the x, and this the y. So we're thinking of the xy plane that we normally would draw this way. When we're talking about 2 dimensions, we draw it this way. Now it's an x. So we're just turning it sideways and we're thinking of this xy plane being horizontal. And we're going to add one more axis here, the z-axis. And right here where they all meet is the origin. All of these 3 axes are perpendicular to each other. And this is our 3-dimensional coordinate system. We have an x and a y and a z. So if we're thinking of our normal x and y, our xy coordinates, the z coordinate, our z-axis, will be coming directly out of the screen right here. That would be our z-axis. So points in 3-dimensional coordinate system are ordered triples instead of ordered pairs, x, y, and z. And we worked with ordered triples a little bit when we solved simultaneous equations. We had 3x3 matrices. We talked about how we could think about the solution to 3 sets of 3 equations as where 3 planes intersect. So that was one way we did this a little bit. We end up with 3 sets of coordinate planes when we talk about a 3-dimensional coordinate system. So we have our axes, our x, y, and z axis, but we also have coordinate planes. So our coordinate planes, we have the xy plane. So down here on this horizontal, we're thinking of this horizontal surface here. On the xy plane, z is 0. And we have this vertical plane over here we call the xz plane, the xz plane. And on the xz plane, y is 0. And then we have the yz plane, this vertical plane here. On the yz plane, x equals 0. So those are our coordinate planes. We can also extend our axes. So this is the positive x, the positive y, and the positive z. I can extend our axes, these axes, the z-axis I can extend down. So we have negative z. Extend back this way so I get the negative x. And extend this way and I get the negative y-axis. So we end up with, rather than 4 quadrants that we had in the xy plane, we end up with 8 octants. So our planes divide space into 8 octants. The first octant is where x, y, and z are all positive. And then we find our other octants by going counterclockwise around the z-axis. So just like we found our 4 quadrants by going counterclockwise in the plane, so we'd have the first octant here where x, y, and z are positive. Our second octant would be back up here, third octant over here, and the fourth octant here. So our first octant 1 through 4 are in the same place as quadrant 1 through 4 on our XY plane. So we go counterclockwise around the z-axis. And then the fifth octant, so we have octant 1, 2, 3, 4. The fifth octant is below the first octant. And then again for octants 5 through 8, we go counterclockwise around the z-axis. So for the most part, it's not that important that you know where the sixth octant is. Usually we'll be talking about the first 4 octants, and we do in Calc 3 we do a lot of three-dimensional stuff, and for the most part we're working in the first octant or the first and second octant, sometimes in the first 4, but it's not that important that you know, okay, the 7th octant is down here below the XY plane when z is negative. You can figure it out. You should be able to figure it out just by using this information, but just be aware that we have 8 octants. We start where x, y, and z are all positive, and we go counterclockwise around the z-axis. So is everybody good with our octants? When we set up our coordinate system this way, we call it a right-handed coordinate system. And we're only going to work with right-handed coordinate systems. And the reason we call it right-handed is if our thumb points in the z direction and our finger points in the positive x direction, our palm points in the y direction. So our right hand, our thumb would point in the z direction, fingers point in the x direction, and our palm points in the y direction. So that makes a right-handed coordinate system. Left-handed coordinate system, we end up with one of the axes reversed, but we're always going to use a right-handed coordinate system. All right, we good with the idea here? I had an eye test a few weeks ago, and on the test there was a little star pattern that looked kind of like this, with just dotted lines, and all I could see, I didn't see stars. Didn't see the star, I saw the X, Y, and Z axes going across the screen. All right, so let's plot some points. Let's plot some points in a 3D coordinate system, and then we'll talk about some formulas, some familiar formulas. So we want to plot. I'm just going to write these 3 points. Plot 3, 2, 3. -2, -1, 3, and -4, 4, 1. So I'm going to draw my axes here, and we'll plot these out just to get an idea of how we want to visualize points in 3 dimensions. So I'll draw my negative axes in dotted lines here. And this is our z, this is our y, and this is our x. So the point 3, 2, 3, we plot it just like we do in the xy plane. I'm going to go 3 units in the x direction. This is x, y, z. 3 units in the x direction. 2 units in the y direction. And then 3 units in the z direction. So I'm going to go 2 units here, 3 units here, 2 units there, and 3 units up. So that would be 3, 2, and 3. So that would be the point 3, 2, 3. And if I put a dotted line over here to the y-axis, parallel to the x-axis, we would hit the x-axis, or sorry, the y-axis at y equals 2. This is at x equals 3. And up here on the z-axis, if I went over here, this would be z equals 3. So I'm going over 3, over 2, up 3. So let's plot this next one. Get a solid line here. Do my dotted lines for my negatives. And this is my z, my y, and my x. So for this one, I'm going to go -2 in the x direction, so I'm going to go 2 units this way. I'm going to go -1 units in the y direction, so 1 unit that way, and then 3 units up. That would be -2, -1, 3. So I went 2 units in the -2 units in the -2 units in the x direction, -1 unit in the y direction, and then up 3 units. And then finally, let's plot this last one. So we got my z, the y, the x, and we're going to go -4 units in the x direction. I'll do this one in green. So we're going to go -4, we're going to go 4 units that way. We're going to go 4 units in the y direction, in the positive y direction, so I go 4 units that way. And then go up 1 unit. So that would be -4, 4, 1. All right, everybody okay with how we find our locate our points in space? And then just as a kind of a preview, we in 3 dimensions, we just finished talking about polar coordinates. In 3 dimensions, we talk about cylindrical coordinates and spherical coordinates. So we can have a different set of coordinate systems than the x, y, z. And we talk about angles and radii. So we can get several different kinds of coordinate systems that can be useful in 3 dimensions. All we're going to talk about here is rectangular coordinates. All right, so we all good with our points? All right, so let's talk about the distance formula and the midpoint formula. Our distance formula and our midpoint formula exactly the same as they are in 2 dimensions. We just have z added. We just add one more piece to our formula. So if we have points, our points are x1, y1, z1, and x2, y2, z2. The distance between them is a square root. x2 minus x1 squared plus y2 minus y1 squared, just like in 2 dimensions, same distance formula, plus z2 minus z1 squared. Exactly the same thing. We just have three quantities we have to calculate inside our square root rather than 2. and our midpoint between these 2 points. Just like our midpoint formula in 2 dimensions, we have the averages of the coordinates. x1 plus x2 divided by 2, that gives me my x coordinate. y1 plus y2 divided by 2 gives me my y coordinate. And z1 plus z2 divided by 2 gives me my z coordinate. Just like in 2 dimensions, we just have this extra piece to take care of the z coordinate. So I'm not going to do a lot with calculating with these. We should be fairly familiar with them. We just add this one piece for the z coordinate. Questions so far? All right. Let's get to something a little more interesting. The equation of a sphere. So we have a sphere, we have our center, H, K, J. And our radius equals r. So a sphere in space, we say a sphere is the set of all points that are equidistant from a given point. Our given point is a center, and our distance is a radius. So anyone want to guess, since we just finished an entire unit on conic sections, and the circle is a conic section, guess what our standard equation of a sphere is going to be. X minus h squared, y minus k squared, z minus j squared, equals r squared. R squared. Squared. So let's think. So our question was, why wouldn't we cube it? What we said the equation of a sphere was the set of all points that are the same distance from the center. What is this x minus h squared, y minus k squared, z minus j squared? Where does that come from? That's the distance formula. If I go back here, that's the distance formula. The distance they are from the center is the radius. So if I square both sides of this, I end up with this. So this is just the distance formula. The equation for a sphere is just the distance formula in 3 dimensions. So that's why we end up with everything squared. So let's look at a couple of examples having to do with a sphere. Let's start with an easy one. And this is the standard equation, by the way. Standard equation. Equation of, for this example, we want our sphere. This is very easy, hopefully. X, so our center is at 2, 3, negative 1, and our radius equals 5. So what's our equation going to be? X minus 2 squared plus y minus 3 squared plus z plus 1 squared equals 25. Nice and easy. Just like circles. Spheres are very nice surfaces. Alright, let's make it a little more complicated. So we want the standard equation of x squared plus y squared plus z squared minus 2x plus 6y minus 4z minus 2 equals 0. We have to complete the square 3 times. One's for the x, one's for the y, one's for the z. Minus 2x, yes. And we know it's a sphere because we have an x squared, a y squared, a z squared. They're all added, they're all positive, and the coefficients in front of each are all the same. So we have a sphere. So we have to complete the square 3 times. Just when we thought we were done completing the square. So let's group our x terms. X squared minus 2x plus y squared plus 6y plus z squared minus 4z equals 2. All right, so let's complete the square on the x. X squared minus 2x, what completes the square here? Plus 1. Half of 2 divided by 1 is 1. 1 squared is 1. X squared plus 1 plus y squared. And I'm going to put this over here. Equals 2 plus 1. I'm going to add the 1. Y squared plus 6y. What completes the square here? Plus 9. I'm going to add the 9 there. Plus z squared minus 4z. What completes the square there? Plus 4. And I get x minus 1 squared plus y plus 3 squared plus z minus 2 squared equals 16. So we know our center is the point 1, negative 3, 2, and the radius is 4. So not too bad. We didn't have coefficients on the x, the y, and the z, so that made it pretty quick and easy. All right, a couple of things about surfaces. So we call a sphere, we call the graph of this thing a surface in 3 dimensions. The surface is just the points that are on the sphere. It's not the inside part, it's just the points that are on the surface. So it's not everything inside, it's just like the shell. So when we talk about a surface, if we graph this, we would be graphing a surface. And our surface is just the part that's on the outside, not the part that's on the inside. Questions there? All right, one tool, the last thing we need to talk about today, one tool that we use to help us visualize surfaces in 3 dimensions, when we have something a little more complicated, and I'll talk about that in just a second, a little more complicated than spheres, is we call the trace. The trace of a surface. And when we're talking about the trace, we want the intersection of the surface and one of the coordinate planes. Or we could talk about a plane that's parallel to the coordinate plane, but usually we're interested in the coordinate planes. So we want to know what our intersection looks like. And we call that a trace. And like I said, it could be usually we talk about the coordinate planes, but we could also talk about planes that are parallel to the coordinate planes. So what if we wanted the trace the xy trace of x minus 4 squared plus y plus 3 squared plus z minus 1 squared equals 25. So we want the trace in the xy plane. Now let's make it more interesting. Let's do the xz plane. Well, this is a sphere, right? And we want the intersection in the xz plane of the sphere. So what are the possibilities? If we talk about how the xz plane is going to slice this sphere, what shape are we going to get? A circle? Or what else could it be? A point, if it's just tangent to the plane? Or what else could happen? It might not intersect it at all, right? If it doesn't touch the xz plane, there would be no trace. There would be no trace of the sphere in the xz plane. Well, how are we going to do this? What do we know about the xz plane? Y is 0. So I'm going to substitute y equals 0 and simplify. So I get x minus 4 squared plus 0 plus 3 squared plus z minus 1 squared equals 25. So I get x minus 4 squared plus 9 plus z minus 1 squared equals 25. And I simplify this, x minus 4 squared plus z minus 1 squared equals 16. So I get a circle in the xz plane. The center of the circle in 3 dimensions is 4, y is 0 on the xz plane, and 1, and the radius is 4. So the sphere intersects the xz plane in this circle. All right, we good with that example? So really, all we're going to work with here is spheres, but the trace in the coordinate planes helps us with all kinds of surfaces. We do in Calc 3 right now. This entire semester we've been doing all these different shapes in 3 dimensions. So let me talk about them real quick. This is not something that's going to be in your homework. Just kind of a preview of what you end up doing with these things. So our sphere, this is the standard equation of a sphere. We talk a lot about surfaces called paraboloids. And the equation of a paraboloid, if we have our center at the origin, is z equals x squared plus y squared. So when y equals 0 in the xz plane, we have z equals x squared, a parabola. When x equals 0 in the xz plane, we have z equals y squared, a parabola. And we end up with a surface that looks like this. So the sides are parabolas. And then if we go parallel to the xy plane, so z is a constant, we have x squared plus y squared equals a constant. So we get circles around here. They get bigger as we go up, as z gets bigger. So this is a paraboloid. And we talked about the reflector of a flashlight. So the surface that's the reflector of a flashlight is a paraboloid. So the sides are parabolic all around, and then it's a circle this way. So that would be a paraboloid. And the traces in the coordinate planes are parabolas. So that helps us visualize that. We can also have an ellipsoid. An ellipsoid, we're going to have an equation with our center at 0, 0, 0, x squared over 5 plus y squared over 9 plus z squared over 11 equals 1. So when z equals 0 in the xz plane, we have an ellipse in the xz plane. Same when y equals 0, same when x equals 0. We have ellipses in each of our planes. So an ellipsoid, if I graph just the top half of it, let's see, our y-axis, so we ended up with a shape that looked something like this. YZ is going to be bigger. So this would be the top, kind of the top half of this surface. So it would kind of look like a squished sphere. We squish it this way and squish it this way. So kind of a football shape. A football shape would be an ellipsoid. And then we can also, and the traces in each of the coordinate axes are ellipses. That helps us visualize this thing. We can also talk about the equation of a cone in 3 dimensions. Z squared equals x squared plus y squared is a nice easy cone. In the xz plane, when y equals 0, I get z squared equals x squared. Take the square root of both sides, I get z equals x. So the equations, the trace in the xz plane is a line. Same thing in the yz plane, a line. And when z is constant, I get x squared plus y squared as a constant, or circles parallel to the xy plane. So this would be the equation of a cone in 3 dimensions. We can also have hyperboloids, different kinds of hyperboloids, and hyperbolic paraboloids, and all kinds of interesting shapes that we can talk about the traces in the coordinate plane. So the trace is a really useful tool for helping us visualize these things. All right, questions? All right, I love visualizing things in 3 dimensions. 3 dimensions is so much more fun than 2 dimensions. All right. There was one of the first shirts for Calc 3 said 2 dimensions is for squares.